Hi everyone, welcome to GEMCHEM. Now today's video is on stereochemistry part 11 video, and here we are going to deal with heterotopicity and NMR. Now before starting, already 10 videos on stereochemistry are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present about this video. And if you are new to GEMCHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So when we talk about topicity, we have homotopic, enantiotopic and diastereotopic. In the previous videos, I have explained it in details. So when a proton is homotopic with another proton, whatever may be the environment or solvent, they are always isochronous. What does that mean? Suppose two protons are attached to a carbon. They are homotopic to each other. So they will have same chemical shift. That is, singlet will be obtained. In case of enantiotopic, we are going to see that there will be two protons which are enantiotopic. Isochronous is being obtained provided we are running the NMR in a symmetric environment. So we can say they are usually isochronous, but once we are running the NMR in a disymmetric environment or solvent, or if we are using any kind of Schiff reagent or chiral solvent, then the enantiotopic protons gives us anisochronous NMR. That means you are going to see that there will be shifting of the signal and there will be quartet observed. Next we have diastereotopic. In this case we are going to always see isochronous shift is being observed. We are going to discuss some molecules and see how their spectrum are being obtained. So first we have this moiety. We have HA and HB. From here only you can understand that these are placed in one single carbon. These are geminal hydrogens, and since there is no mirror image relationship, so in this case these are diastereotopic since they are present in two different environment, and so we will have anisochronous shift and these will appear as two doublets. So the appearance will come to be like this. You have this one, you have another pig and another pig. So this is known as AB quartet. So Q is written in small. So this is the spectrum, and for these two proton we have the particular region as this part. So here we are obtaining ABQ, that is AB quartet. Now we are going to shift for our next molecule, that is this one. So here we know that chirality is present due to chiral axis, and we are going to discuss this hydrogen and this hydrogen. So these are two also diastereotopic in nature, and we are going to see an isochronous shift. Here also we are going to obtain AB quartet. Next molecule is this one. In this case you can see that one Br is present this side and CO2H is present this side. Again this becomes a diastereotopic and the shift will be anisochronous. We are going to get ABQ. So if you consider here, this is a little bit very fine structure. So here you are going to get a quartet. This is your quartet structure. Now when we shift for our next moiety, this is the next one. This has the two protons HA and HB which we are going to consider. So this is N-benzyl 2,6-dimethyl piperidine. This is cis 1 which we are considering. This can be written in chair form like this. And for this one, for the cis, this is the cis, and the two protons are enantiotopic in nature. For that case, we are going to see that isochronous shift is being obtained and it is a singlet. So from here you can see the peak for this one, and here we have only a singlet obtained. So we can write it appears as singlet in NMR. When we shift for the next one, we have this trans one. In this case, HA and HB when we draw in chair form, this is actually diastereotopic in nature. We are going to get an isochronous shift. As a result, ABQ quartet is being observed. This presence of pH will cause the splitting into quartet. So here we can see diastereotopic, anisochronous, and appearance as AB quartet. Now this one is our work to find out. So when we are considering this particular molecule, from here we can see that there are 3 prochiral centers. These are the 3 prochiral centers. Now when we consider these 2 hydrogens, these are actually diastereotopic. We can write them as diastereotopic, as well as they are actually anisochronous. So you know what you are going to get, what type of pick, that is ABQ. That will, it will appear like this. So this is for these 2 hydrogen. And the important part is that here the particular member is having a pH here. So this ABQ quartet, due to the presence of pH, can further split up and give you multiplate. There is a chance of formation of multiplate. Now when we go for the next molecule, we have this one. Similarly, we have 3 prochiral centers, as you can see, and in this case also the 2 hydrogens which are present here, this one and this one, is diastereotopic. Similarly, we can tag them as anisochronous, and these will provide you quartet, but since there is a presence of pH here, there can be formation of multiplate, complex structure in the NMR spectra. When we are talking about the CH3 present here, that is this one or this one, then what happens is there is formation of multiplate. One signal divides into 2, and that signal further divides into 2 more. So here also quartet is being observed, but for this CH3 and this CH3. So these were the different examples required to be discussed with NMR and heterotopicity. Hope this was helpful. In the next video, we are going to deal with isogamy and anisogamy. So thank you for watching. Do not forget to like, share, subscribe and comment.